It's been quite a while since my last video. Um, just doing the normal summer things with the family, vacations, traveling, whatnot. But I've finally gotten a chance to get this amplifier finished and do the last video in this build series here to show the progress that's been made on the amp. As you can see, it's all put up together now with the cover on. And in a minute here, I'll take the camera off the tripod and we'll look at some of the things that have been done inside the amp to finish it. I just wanted to kind of see the overall completed amplifier here. As you can see, we've got tone controls up on the top portion here. And the front panel is pretty simple. There's an indicator here for the speaker protection, and we've got a volume control knob here, and then this is our three-way switch here to control the way the amplifier behaves, whether it's in the switches in the up position. Of course, it would be in an automatic mode to turn on and off with the presence of an audio signal. In the center position, as is shown here, it's off, and in the lower position, it overrides the automatic circuitry, so it just turns the amplifier on, and the amplifier just stays on continuously in case there's some reason that will be desired. On the I'll turn the amplifier around here, and we'll take a look at the back portion. As you can see, not too much going on in the back. We've got our output transistors, our input jacks, output connections for the speakers, got a line fuse and a line cord here. Got the camera off the tripod here so we can just take a look a little bit closer up. Our front panel controls again, and this is a two-way LED. It's a red and green LED, and we'll look at the way that operates here in a few minutes. And then of course our overdrive indicator here, and then we've got bass and treble and bass controls here with some indications here. I've got them centered right now, and our function switch down here. And this green LED here will just light whenever the unit is powered, whether it's on or in standby. As long as this is not in the center position, this green LED will be lit. All right, like I said, used some of this steel, perforated steel sheet here to make a cover cage for the amplifier, just to let it sort of breathe a little bit. It does get, there's some power in this unit, so it does get a little bit warm, not in anything of significant heat, but just with power electronics, they do produce some heat, just to let it sort of breathe a little bit. And kind of redid this mounting system here. This is just a piece of aluminum stock that threaded, and I've got it spaced so that in order to remove this top cover, it's pretty simple. You just take these two screws out, and then this will slide, and then the whole cover will come off, so that everything is accessible there inside the amplifier. We've got the cover off now. Let's take a look. As you can see, quite a bit of work has been done in this amplifier since the last video, and we'll talk about some of the things that ended up changing here on the amplifier. First thing you may notice is that I redesigned the power supply here. I didn't really like the way that the original design was working. There was too much of a delay on power up, and it really was kind of overly complicated. So I really kind of changed it, simplified it out some. Got rid of the delay circuitry there on the low voltage side. So as far as the unregulated supply, we've still got the the two reservoir filter capacitors here. We've got fuses here for each channel independently. And for the low voltage side, for the 27 volts, changed the regulator out. It's no longer just a Zener diode and a pass transistor. Actually used a, this is a LM317 adjustable voltage regulator. This is the high voltage, the HVT version, just because of the higher input voltage coming into this regulator. So we used a high voltage version, but it's an adjustable regulator, but I've got it set at a fixed value with just some resistors here making a voltage divider, and it's set for approximately 27 volts. So that's the change there. Now, I did keep the delay, but I moved the delay, the inrush delay, to the AC side of the supply instead of the DC side. For one reason, as on the AC side, there's a much smaller current surge because it's on the AC side, and it's AC instead of DC, so it's going to be easier on the relay for switching in for the inrush delay. And that's what this relay is right here. And we'll take a look at the schematic. We'll talk about how that works. This is a DP-DT relay here, and we're using that relay for two functions. We're using the relay, one side of the relay we're using to provide an inrush delay for unregulated supply, and the other side of this relay is being used to switch the AC to the speaker protection board, which is here, because that speaker protection board uses it senses the presence of AC to let the speaker protection board know that the amplifier is turned on, and we'll talk about that when we look at the speaker protection board. But so while we've got it here, this is the new speaker protection board. So I've changed out the speaker protection circuitry, and we'll look at this circuitry and talk about it too. But let's take a look at the delay first. All right, so this is just a soft start delay. It's a generic circuit. It's not, I didn't design it specifically for this amplifier. It's kind of just one that I've designed for generic use, and I've got it sort of tailored right now to work for this amplifier. As you can see here, this circuit is line connected. The line comes in here, and the delay circuit is powered from the line. There's no isolation from the line circuit. So if you are going to, if you decide maybe you want to build this circuit or you want to experiment with it, just be aware that this circuit is line connected. There's no isolation transformer here for the low voltage portion of this circuit. So definitely be careful, and don't go sticking your ground referenced oscilloscopes on any of these points here. You'll really mess that oscilloscope up if you do. But anyway, so let's talk about how this works. So we've got a line voltage coming in here, and it's when power is applied here to this line connection here, we see that the load is immediately powered through some soft start resistors here, and these will inrush, or these will limit the inrush current here from our transformer. Now I've got it two options here. This circuit here shows using a couple of as a 2-watt 2512 outlined resistors. Now I didn't use those for this circuit because the inrush is too much. It's these resistors are not rated for enough to handle enough power. So what I've done is, and it's pretty simple to do. You can just omit these resistors from the schematic, and you can connect an external limiting resistor across these terminals here, and that's what I've done for this build here. You can see here's the external limiting resistor, and that's a That's a 10 watt, 10 ohm resistor. There's like a metal oxide resistor down there just to limit. It's got much more current power handling capability in these 2 watt resistors here. But so anyway, so that's initially the state of the power. So your load here, your line here, initially powered through your limiting resistor to limit the inrush current, because this relay here is not connected to bypass that resistor. Now what happens is, so over here on this side, at the same time that you've applied power to the relay, we've got a circuit here that drops this voltage down. It's going to go through a couple of current limiting resistors here, a diode to give it some rectification to convert it to DC. You've got some filter capacitors here, and a Zener diode down here, which is going to regulate the voltage at this portion of the circuit here to, I believe this is it's like a 6.2 volt Zener diode. So it's going to regulate the voltage here to about 6 volts. And that's going to power up this timer circuit here. I used a TLC 555. It's a CMOS timer just to again minimize, you've got a lot of drop here across these resistors, so just to minimize any wasted power in this circuit. I really wanted to keep the demand on this low voltage side just as low as possible, so that we could minimize any kind of excessive dissipation here across these resistors. But and this timer is configured as an on-after delay. So when the timer's powered up, it's going to initially power up with the output in the off state. Once the delay is met, it will turn on the output of the timer here at pin 3, which goes through a triac optocoupler here. This is the LED emitter portion of the optocoupler, and this is the output triac portion here. That LED inside this triac, and this side, this optocoupler will turn on. It'll turn on the triac here, pick up the relay, and then the relay will bypass around the current limiting resistor here, allowing full current to flow to the load. And the delay that's set up here is about half a second, so about 500 milliseconds. Long enough to limit the inrush delay, and not too long as to cause any unnecessarily lengthening the turn-on delay for the amplifier. There's a red LED here. This LED lights up momentarily when the timer is in the off state. So on initial power up, this LED will turn on momentarily, and then once the timer switches to the on state here, this LED will turn off. So this LED is only on momentarily, and that's, that can be omitted, that portion here. I liked having the ability to just check the relay to see the status of the delay, and that's just a visual indication there. And that LED is on the board. It's on the back side, so you can just, when you turn it on, you can see it shining through the board here. But it's not a panel indication here. It's more just a sort of an observation or a diagnostic sort of thing. All right, so that's the delay circuit here. So like I said, moved it from the DC side to the AC side, and this is the new delay relay. Now this is fed, this relay is fed through the relay on the preamplifier board that is used to detect the presence of a signal. So when a audio signal is presented on the input of the amplifier, and the delay circuit that we looked at on the previous video detects the presence of the audio signal, it turns on the relay. Then that relay completes the circuit to power up the amplifier here through the delay relay. So this is powered, then there's a short delay to limit the inrush, and then the relay turns on here to bypass the inrush limiter and provide full power to the amplifier. All right, so we'll take a look at the speaker protection circuit here. So before I go into the description of the circuit here, I want to give credit to the designer of the circuit. This circuit was taken from a website. Here's the website here, Elliott Sound Products. he's got a they have a really great website there with lots and lots of audio projects, all kinds of different audio projects, amplifiers, preamplifiers, different protection circuits, mixers, tones, all kinds of stuff there. And so that's where I got this original circuit for. Now this is not his original design. This has been modified as a bi-directional opto isolator. So has had some changes. I also added a this is the LED driver for the dual indicator LED for this for the front panel. So this is some modifications to it. You know, with the original design of this speaker protection circuit, it's basically I wanted the protection to actuate at a lower voltage. The original design, it would actuate somewhere around 4 volts DC to the speaker terminals, and I wanted it to actuate at lower. So this design now has it actuate at about 1.2 volts. So just at the forward voltage, forward bias voltage of the LEDs inside this opto isolator will actuate the speaker protection relay. Now, so anyway, like I said, so this is where the original circuit came from, and you can check that website out as you so desire. Now, for this amplifier, you know that this Heathkit amplifier is capacitively coupled to the speaker, and so that makes putting a speaker protection system into this amplifier a little bit trickier, because on power up there is going to be the presence of some DC here on the output of these capacitors, until as these capacitors charge up when you power the amplifier up, there's going to be DC here. Now they will go away quickly, but you do get some DC at the speaker terminal initially when the amplifier is powered up, and that's where you get that sort of pop or the click sound when you turn on your well, like if you have an AR 15, a Heathkit AR15, you'll know when you turn the stereo on, you get that little power on thump, that click. That's because these output capacitors are charging. And if you've got an amplifier that operates capacitively coupled, then you know that if the speakers are connected when you power up, you'll get that sort of turn on noise. And that's, again, like I said, because initially there is some DC here until these capacitors get charged, these output capacitors. So in order to get the speaker protection to work right, I had to create a discharge or a charge path for the capacitors. And that's what this relay does here. So these are DP-DT relays. And initially, when the relay is in the disconnected position, as you see the speaker is connected to ground, and the output of the amplifier is connected through 10 ohm resistors which go to ground. So this provides our capacitor a charge path so that it charges quickly. Without these resistors here, what happens is these capacitors take quite a long time to charge and for their charge to stabilize to a constant value. And that's because, you know, when Heathkit originally designed this amplifier, they assumed that you would have a speaker connected here all the time, and so the charge path for these capacitors would be through your speaker. And that's where you get the click or the pop sound as your capacitor is charging. But when your speaker is not connected, as it is here, it takes, like I said, it takes a while for these capacitors to stabilize in a charged state. So that's what the resistors here do, is they sort of take the place of the speakers until the coupling capacitors get charged up. And that's what these resistors are here. These two resistors that are mounted up on these standoffs are there to allow the capacitors to charge on startup. Now, so you may wonder why these are up here. Well, so I wanted these to act, you know, these kind of act sort of like fuses. So what happens is if you have leakage across your output capacitors here, and that causes the speaker protection to actuate, which will isolate the speakers. Now you're going to have voltage here at the output of your capacitor, which is going to go through these resistors. So if that voltage if that voltage is high enough, it's going to burn out these resistors. And I didn't want the resistors to be, if they burned out, I didn't want them damaging the board, causing shard marks on the board, or I didn't want them to be too difficult to replace if that happened. So I put them up here on these standoffs. So what'll happen is if for some reason one of these capacitors starts leaking DC voltage, and of course the relays will actuate to isolate the speakers, but then these resistors will just simply burn up and they'll fail, and this shouldn't cause too much damage to the surrounding components of the board in the process. And then you'll have the visual indication of which channel it was that failed, because it'll be the one with the burned up resistor. Probably not both channels simultaneously, but one of them could fail. Anyway, when that happens, your speakers will be safe, and it will be easy to repair, because you simply have to change the capacitor and the resistor, and you can do that all right here without having to disassemble the amplifier or do anything like that. All right, so taking a look at the speaker protection circuit here, we've got an input voltage. Now this input voltage is from the high voltage unregulated supply from the amplifier, and it goes through a fuse and then through a simple regulator here. Use a high voltage transistor and a 24 volt Zener diode to regulate the voltage here down to about 24 volts. This transistor does get fairly warm, and as you can see, we got it mounted to a heatsink here, so that heat can be dissipated away from the transistor. There's an AC monitor here. That's the yellow wire here, and that's the one that we used the other side of our soft start relay here. So what the AC monitor does is the AC monitor looks for the presence of AC going to the power amplifier. That's how it gives it a little bit of intelligence to tell the speaker protection that, hey, the amplifier is turned on, and that's what this does. So it monitors the AC. When it detects the AC, the speaker protection knows the amplifier is turned on, and that it should actuate when the voltage at the speaker terminals is at an acceptable level. And all this does here just rectifies it, sends a pulsed signal to turn on this transistor here. All right, other than that, we've got basically a transistor network here that controls that. What it does is it controls the two speaker relays here. There's a delay circuit here to give the speaker protection circuit some turn on delay. That's supposed to minimize that turn on thump. So when you turn your amplifier on, it detects the presence of AC. After a short delay, I think the delay is maybe like 2 to 3 seconds, then it will turn on the relays to connect the speakers to the output of the amplifier. And the idea is at that point the voltage, the power amplifier voltages have stabilized to a point where it's not going to cause any loud turn-on transients. The optical isolator here will turn on if we get a DC voltage here on our speaker lines. We'll turn on the LED for whichever channel it is, and it will actuate this transistor here, which will then cause the relays to de-energize, and will switch our speaker to ground to protect the speakers. This relay is shown in the de-energized state here, so that you can see the speaker is normally connected to ground, and this relay has to be energized in order to connect the speaker to the output of the amplifier. So again, a little bit of a fail-safe design there. If for some reason something happens in this circuit and the relay is de-energized, it will protect the speakers, so the speakers are connected to the ground there. Now we've got 24 volts here, so we've got two 12-volt relays in series, and we've got just some back EMF protection here on the relay coils. All right, looking at this LED indicator circuit here is really nothing too fancy here. It simply turns on the green LED here if our speaker protection relays are energized. It'll turn on a green LED on the front panel here to let us know that the speakers are connected to the amplifier. And if not, the red LED, the green LED will turn off and the red LED will turn on to let us know that either the speaker protection has actuated or the relays are not closed for whatever reason. What will happen here is as when the amplifier turns off, like when it's in automatic and it turns off in the absence of a signal, the speaker protection relay will turn off to disconnect the speakers, and this red LED will come on to let you know that the speakers are disconnected. And actually what will happen is it'll come on and it'll start to fade out as the filter capacitors here are discharged, because it is they are basically acting as sort of like batteries as they discharge, and they continue to power the speaker protection circuit. All right, so that's our speaker protection circuit here. We'll take a look at this board. I did decide to go surface mount again just because I had some limited space and trying to get all the components here in our limited space. But it worked out pretty good. Now, what you can't see is the relays, and the relays are actually mounted underneath the board. You can just see one of them right there. And because they are mounted upside down, it does require them to have a little more pull-up current to ensure that they latch properly when they get energized, because they're latching against gravity. So I had to play with the value of this resistor here, which is the current limiting resistor for the relays. Now it says in the schematic here is 390 ohms. And what I actually found was I had to get it down to 180 ohms in order to get the relays to pick up reliably, because they're mounted upside down. And at the same time, not to be picked up so much that they required an excessive amount of turn-off time. So if they're when they're turned off, there's going to be a little bit of a delay. So if they're turned on with, if they're turned on, I guess, with more current through them, then they will have a tendency to open. There'll be a little bit of delay to opening. So the idea is you want these relays to open quickly, because that's going to help you minimize your turn-off transients on your speakers. But you want them to be able to have sufficient current so that they close, in this case, against gravity. Now, if you might mount these relays like they're standing, right side up, then that wouldn't be so much of a problem here. But just because of the way this board is laid out, I had, my full traces on top, and I can't make plated through hole circuit boards at the house, so just had to figure out the best way to get this arrangement done, and that's how they were done. So anyway, but like I said, I played with the value of this resistor, and I found that 180 ohms worked out very well. It makes sure that the relays turn off quickly enough to avoid a transient on turn off, but that they have a sufficient current to draw in to make sure the speakers get connected when the amplifier turns on. Also on the bottom is the coils, the chokes here that are part of the original Heathkit design. So there's the coupling capacitors and then the output chokes here. Again, mounted on the bottom. You can just see one of them right there for space concerns. And we got our opto isolator and our input filter network here for monitoring the speaker terminals. And this filter network will basically ensure just about all the way down to DC will be present here. Now, I think the cutoff frequency for this network is about 3 hertz. It's the same filter network that the original designer at Elliott Sound Products used, and I believe the 100 kilo ohms with the 10 microfarad capacitors gives a turn off or a frequency response to somewhere at the upper range of like 3 hertz. So I don't I don't suspect there's going to be 3 hertz of audio going through this amplifier, but it'll respond all the way down to 3 hertz from DC to about 3 hertz. And at that point, so that'll make sure that the speaker protection is not false triggering on a low frequency audio signal. So 3 hertz should give plenty of room to normal audio ranges for listening to music or whatever. All right, so I'm going to connect the amplifier up to a dummy load here. We'll take a look, power it on, and see how this speaker protection actually works here to power on, and the sequence that the amplifier goes to when the amplifier is powered on. All right, got the amplifier hooked up now. Just going through a little cheap set of speakers here for just for testing mainly, and a whole bunch of speaker cable there. I've got the hooked up to the isolation transformer, and that's on. The amplifier is off right now, and I'm going to try to play it through some audio through this Walkman here. Now the line out's pretty weak, so I had to find something that's a little bit louder. But that should be good to turn the amplifier on. And so what we'll do is we'll put the amplifier into standby, and we'll see that the green LED will come up there, and you can look on the isolation transformer there. We're pretty much not drawing anything. That's just the basically just the standby circuitry listening for a signal, and I've got the volume turned down. All right, so I'm going to turn on some audio here, and we will see how the amplifier starts up. So we'll go ahead and I got the like I said, I got the volume turned down. So we'll look. This will go turn on. It should start up red initially, and then go to green pretty quick. We'll hear the relays pick up for the soft start delay first, and then the speaker protection relays will pick up after that. So I'm going to go ahead and turn this audio on. All right, so there's our red. And all right, and there's our, so now our speakers are turned on. All right, so we've got some audio, as you can hear. I'm going to turn that down because, like I said, I don't want to wake the whole family up right now. All right, but that's pretty much it. Now what I'm going to do is I'm going to cut this audio off, and I'll probably cut the video because it is a rather long delay for the amplifier to turn off. So just instead of you sitting here and listening to silence for about a minute or so, I'll cut it back to just right before the relay picks up. We'll see how that switches back over. All right, and you can see, as you heard, the relays, the speaker protection relay dropped out, and the soft start relay dropped out, and our LED status here is red, showing that the speakers are disconnected. And this, like I said, will fade away because right now it's just being powered from whatever is being discharged out of these filter capacitors here. So that will eventually fade away here in about a minute or so as that discharges. And then we'll turn the amplifier off. Now, one more thing we can do, we can go ahead and put it in full on. And we see that it turns on right away. And our speakers are turned on there. So now the amplifier is just turned on, and it'll just sit here. Now you can see that, we're drawing quite a bit more idle power here. And that's the reason why I wanted this amplifier to be able to turn itself on and off automatically. There's no reason to sit here and idle and just waste that power there when it's not being used. That's all for this video. I'm glad that I was able to finally get this amplifier finished, and I'm probably going to do some listening to it, let it burn in a little bit, and then as long as no issues arise, then it'll be delivered to my dad and hooked up to his TV set. So that'll work pretty good. I think he'll be quite happy with it. Like I said, he wanted the amplifier to have a certain look to it, and I think he'll be pleased with the way this has turned out. I'm glad that this project is done, because I have been wanting to move on to other projects. I've got a backlog of equipment to repair, so those videos will be coming out as I get time to put them out. So be looking forward to some more, getting back to some more repair, troubleshooting and repair type videos for some equipment I've got. And maybe a little bit later on down and do another, maybe I'll do another build project. Maybe some tube work. I haven't done a lot of tube work recently, so maybe kind of wanting to get back into that. So we'll just see how those things come out. But like I said, be looking for some more troubleshooting and repair type videos coming out here in the near future. If you enjoyed the video, give me put a thumbs up or whatever in there. Feel free to leave any comments for the videos, and be looking for more to come in the future. That's all for this video. Thank you for watching.